jutro in lepo pozdravljeni na fakulteti za naravoslovje Univerze Prva. Ker imamo tujega gosta in predavanja v angleščini, zdaj vklopne v angleščino. So, good morning and welcome everyone to the School of Science faculty at the University of Gorica. I'm sure that we all remember the image of the orange donut that was in all media and circulated the globe, social media and news in April 2019. So that was the first image of a black hole, and it was an impressive achievement because I remember as a student I was told, and I also told that my students, that it's basically impossible to see the black hole. They are very small and they are far away, so it is impossible to see them, to see their shadow in the sky. But the Event Horizon Telescope team managed to do just that, impossible, in 2019. So they showed us the image of the black hole in the galaxy, which is more than 50 million light years away. So today we have a distinguished guest, Professor Heino Falcke, who is Professor of Radio Astronomy and Astroparticle Physics at the Radboud University in Netherlands, and Honorary Doctor of the University of Gorica. He is the chair of the Science Council of the Event Horizon Telescope. He's a recipient of several European Research Council grants, and of course several prizes, including the Univerza Prize, the highest scientific award in the Netherlands. He's also a member of the Academia Europea and Royal Netherlands Academy of Arts and Sciences. So we are honored that today we have such a distinguished guest and opportunity to hear about this achievement, one of the greatest achievements in astrophysics in the last few decades, I would say. So to hear about that directly from such an expert.
Thank you. It's a great honor and a pleasure to be here at this university. I think you're a young university, 20 years old, and my university, also a young university, celebrating 100 years next year, so that's in the Dutch context. But we already collaborated, interestingly, because we've been working on the Auger collaboration together in the similar fields in astrophysics. So I'm glad to be here today and talk you a little bit through how we went to the essentially edge of space and time. And if you go into space, I think that changes our perspective. Every time you look into space or you go into space, it changes our perspective of space and time. And that's an old realization. If you even go to the Bible, it says 1,000 years in your sight are like a day that has just gone by, or like a watch in the night. Time is relative. We know this on a personal level, right? Some days, like if you're on an exam, they take ages, and some things go by very quickly. If you are, I had a program on the Space Telescope, the old one, 20 years ago. You went into space virtually with your mind, preparing programs, and then you have to work with 90-minute days. But also time literally changes when you're going up into space. Time runs faster, and that has to do with relativity. If you send a GPS satellite up into space, you actually detune it here on Earth. It actually goes wrong. And only when you send it up into space, it goes properly, the clocks go properly right. And that has to do with the theory of general relativity that Albert Einstein developed in 1915. The idea that gravity is not a force, but actually it's a property of the curvature of space and time, and that space and time have to be thought together. So if you have a body that has mass, that can also have mass and energy, then will actually influence the space surrounding it, the empty space. And we cannot picture this in our mind, how a three-dimensional space will be changed or curved. That's why we represent it here with a two-dimensional surface. And it's like a bed where you jump in, once you jump in, it will have a little dent. And so every mass that is in space will make a little dent in space itself. And then everything else follows from that. And you see sort of this yellow line supposed to be a a light ray, and the light will follow the curvature of space. Like if you were sort of, having this trampoline, you're lying in the middle, and you try to roll a ball, the ball will follow the curvature of space. The ball itself will also curve space, so space and mass will influence each other, and so it's sort of a dance of space, time, and matter that determines the entire evolution. That leads to very interesting effects. But that also means, and there's another important aspect in that Einstein realized at first in his special relativity theory, and that is there's one particular constant, so to speak, that space and time are not absolute. They are not constant, unchangeable. But what is unchangeable is the speed of light. Everybody always measures the same speed of light. And that's very strange. So how fast I go, whenever I shoot a laser beam, I will always measure it going with the speed of light. And if you are sitting and seeing me going with, very fast, and I'm shooting a laser beam, and I see it going with the speed of light, you also see it going with the speed of light. We see very different things, but we always measure the same speed of light. Now what happens in this case? Light will be deflected. It has to take actually a longer path. Yeah, so that suddenly space has become larger. It still has to take that curve that's with the same speed. So it has to make larger steps. And speed is kilometers per hour, space divided by time. That's what speed is. So if space gets stretched, in order to keep the same speed, you have to stretch time as well. The time you measure will change as well. That's a direct consequence of saying that speed of light is constant. And that has been experimentally verified. That's the speed of light. So you can only have speed of light constant if the other two things, space and time, change, and they change together. That's the basic principle. It's a completely change of mindset that happened. Then came Karl Schwarzschild, who actually was fighting in the First World War. It was said he developed this in the trenches of the First World War. It's not entirely true. It was actually a villa somewhere at the border to France, where he was playing billiard with Wegener, was a guy who developed the continental drift. And so he had some time left during the war while he was calculating bullets flying to work on some other mathematical problems and communicating with Albert Einstein. And nonetheless, he died of the war, right? So, war is no fun, right? So, it sounds a little bit like I'm taking this lightly. No, he took sort of, in this very difficult times, he took sort of some resort to doing some math. And he calculated how would space and time look like if you have all the matter calculated in one single point. And everybody knows this is just mathematics. Yeah? We physicists, and we do this all the time. We just make some assumptions, right? So we'll just assume, okay, there's a room of students here, and we'll just assume they're all spherical. They're just balls, right? So how do they interact? Yeah, we don't take all the details into account. It's in physics called the spherical cows. Yeah, if you simulate cows, you just assume they're spheres, right? So they don't have legs, anything. Just make it simple. And now you have matter, and you say all the matter is in one point. This is mathematically much more easy to calculate. This has nothing to do with reality. We all know this. This doesn't exist, but mathematically it's much easier. That was the thinking. And so Schwarzschild was calculating this, and that showed some very strange result. Namely, if you had light now going near that point mass, the light would actually terminate. It would actually be deflected so much, the attraction and the curvature of space-time would be so strong that light would not be able to escape anymore. It would disappear in this hole in space and time. And there was a region surrounding that when you come close enough to this point mass, that would be the watershed in space-time, that once light has passed this point, it would never be able to come back. And later it was called the event horizon. Why? Because light, as I said, is the only constant, but it's also the fastest speed in the universe, the fastest way how we can communicate. Nothing can go faster than speed of light. So if even light cannot escape, no other information, no other anything can come out of this. And so every event that happens inside a black hole stays inside a black hole. And that was very strange because it meant that there is an inside that physically should exist or could exist, but that could not be measurable. And Einstein thought this was spooky, and he said this, yeah, sure, it's fantastic math. He loved that. He loved the math, but that, of course, in reality, that doesn't exist, right? So that can't form. And even wrote a paper in the 30s that such thing, which later became known as black holes, could not be formed. Turned out that Oppenheimer actually developed the nuclear bomb, showed that Einstein was wrong within a very short time. And now we know that black holes can form. We know it because the universe is not static. Our view of the universe evolved. We know that the universe is a very dynamic place. It evolves like life everywhere, and it changes. And what you see here is a big cloud of dust, and this dust cloud is sort of 100 light years across. It's little smoke. In the old days, people still used to smoke cigarettes, right? So we don't do this anymore. But it's something like this smoke from a cigarette, but on a scale of hundreds of light years. And on the force of gravity, this smoke will actually start to condense and collapse. And we can simulate this these days very nicely in our supercomputers. And it's a major development, of course, in the last 10, 20 years, that many of the processes in astrophysics we simulate very well using numerical astrophysics. And you see here how these condensations of matters become denser and denser under the influence of gravity, and they form stars. A cluster of stars suddenly lights up, and out of this one little cloud is sort of hundreds of gems of new stars and planets have formed. So stars form. And in fact, it's again gravity. Gravity, by the way, is the creative force of the universe. And that's because gravity only knows one direction. It's the weakest of all forces, but it actually knows only one direction. So if all noses are in the same direction, everything pulls in the same direction, even the weakest force can win. And that's what gravity does. And without gravity, there would be no life, there would be no planets, no stars, nothing, because all other forces cancel each other. Gravity doesn't. Gravity only goes one direction. So stars form, and they also can die again after a few million to a few billions of years, but it's typically only the bright ones and the heavy ones that are that really will explode. The fuel is used up because in stars you fuse hydrogen into helium, and then higher elements are also produced in stars, which means most of the stuff that's inside this room, most of the matter was at one point inside another star and was cooked to a new element. And when the brightest stars have used up all their power, they will explode. And what you see here is a supernova explosion that happened, I don't know how long ago, but we can still measure that it's actually expanding with 10,000s of kilometers per second. We see this explosion wave going out, and we still, every day, we see somewhere a star explode in the universe. And you can calculate that then, if the really most massive stars, the central core will be collapsed so densely that gravity will become the dominant force of all other forces, stronger than any nuclear force, stronger than electromagnetic forces, everything. And so then the inner part of a star only knows one direction, collapse. And the more it collapses, the stronger the curvature of space-time is, the stronger gravity is, because you have more matter in a smaller room. It becomes even stronger. So it becomes even more dominant compared to the others. So it can only become smaller and smaller and smaller. There's nothing that can stop it. And it should collapse into one single point. Of course, we think there may be a reason or a point where this will stop. In principle, it should go on infinitely. It becomes infinitely small for an infinite amount of time, at least from our perspective. It's another little secret I tell you. If you are inside this black hole, you're collapsing, it will happen in a finite time. But if you look from the outside, it will happen in infinite time. So it's another crazy thing. But something should be happening at this quantum scale that may stop this. But we don't know. We don't have any theory that tells us what could happen at this scale. So, by all what we know is infinite collapse. And there we think about hundreds of millions of stars in our own Milky Way. Now this is the Andromeda galaxy, our neighbor galaxy, hundreds of billions of stars rotating around a central region. That's how our galaxy should look like. Nova Gorica would probably be somewhere here on this scale. And it takes us 200 million years to go around. So if you now sort of put a flag in the ground in space and then you wait 200 million years, you should come back here. Not entirely, because in the meantime you'll be tucked around by other stars in the galaxy. You'll never come back to exactly the same place. And of course there's no ground to plug your flag into. But anyway. And of these hundreds of billions of stars, only a small fraction will turn into stellar mass black holes, but there'll still be hundreds of millions. And then if you go to the very center of a galaxy, the density of stars is very, very high. Here we have one star every 4 light years, roughly. That's the distance to the closest star in our neighborhood. But there you have millions of stars within the same regions, millions of stars. And so what will happen is that the most massive stars actually will sink towards the center. The black holes will start to sink towards the center. They will start to merge. And if there is one big one, it will actually swallow the other ones. And so that one big one will become bigger and bigger and bigger. That's at least one way to make a very big black hole in the center of a galaxy. And so the expectation is that somewhere in the center you have a really, really big black hole that starts piling up. And that has been confirmed over the last decades. This, what we see here, is a picture of our Milky Way in the optical with a telescope made by ESO. And what you see here are these dark patches. These are the dust clouds I just mentioned. Out of this, stars will form. That's why sort of most stars form in the disk of a galaxy. We cannot see how our galaxy looks from the top because we are sitting inside. Yeah? So we would have to fly out a few thousand light years to actually get the nice view we had before. So we can only imagine this in our minds, but we can look from the side. We cannot see where the center is because there is a dark cloud in front of it, and that was the problem. Until the 50s, we didn't know where the center of the Milky Way is. Only until we had radio waves, which would pass through the dust, we actually could see the center. But it took a long time to realize this. Now we can also use near-infrared. And so this is a constellation of Sagittarius. And then we zoom in, and now we switch over to a near-infrared light. And near-infrared light also goes through the dust. And what you see now are the central region of our galaxy, where there are again millions of stars. And the very center, this is an image is taken by the group of Reinhard Genzel in Garching. And you see the stars over 16 years. And you see they're moving. Stars are moving there. And the closer you come to the center, the faster they move. And this one up here actually moves with 8,000 kilometers per second. And it goes around on an elliptical orbit. So if you go, you're on the highway and you take a turn and you go with 8,000 kilometers per second, you need very good tires or someone who really keeps you tight, right, to keep you from flying out. And so you can calculate how much force is needed to keep a star on such an orbit. And, well, the only force we know that can do this is gravity, really. And so you can calculate how much gravity is necessary, how much matter do I need. And you find I need 4 million times the mass of the sun. Yeah, 4 million times the mass of the sun needs to be concentrated in this point. And so that was the idea that, that region there should host the supermassive black hole in our galaxy. And that's something that started to emerge when I did my PhD. Sort of this wasn't measured. It was just, the first indication for us we might start to measure something, right? So the idea was there, but this wasn't there, and what I will show also wasn't there. This is now the same region shown in the radio. As I said, in the radio, light goes through the dust. And that's the beauty of radio. I mean, you can use your cell phones inside a house, and you can use your cell phone also inside the Milky Way because it goes through the dust as well. And so this is the plane of the Milky Way. It's glowing in radio light. These are hot electrons deflected by magnetic fields or deflected by ions. And this is the central region. It's called Sagittarius A because A means the brightest radio source in the constellation of Sagittarius. And that was identified to be the center of the Milky Way. And it's actually a supernova that exploded 40,000 years ago. So some of our ancestors had they had radio telescope, would have seen something completely different. And so on cosmic timescale, this is nothing, right? So this looks it will look very different. I mean, the future generations, like in this university in like 20, 60,000 years, will see a very different picture of this region. If you zoom in, you see what's called Sagittarius A West. There's a streamer of gas. In the very center, there's a little spot of radio emission, which is a lot of radio emission coming from the central region. That was already discovered in the 70s. In fact, that was the first prediction where people said, oh, there in the center of our Milky Way, maybe that is the supermassive black holes. And then later came the stars. But we didn't know. I mean, when I started, there was still lots of discussion. People said, oh, maybe it's not a black hole. It can't be a black hole because there were some smart arguments why it couldn't be a black hole. So it was a bit discussion, is this really a black hole? And I wanted to get clarity, and I wanted to see it, right? So can you see it? And I was working in an institute where I was doing theoretical astrophysics, but it was doing also, it was mainly doing instrumentation and observation. So it was, it was doing the experiments. And that's the best place to be. As a theorist, be where the experimentalists are. Because then you can learn what is possible, what are the opportunities you have, what is realistically possible. But you also, you learn how to understand the astrophysics, and that's important. So I realized during my PhD that a certain light, a certain radio frequency would come from near the event horizon. So I wrote some papers said that the radio emission at a frequency of a few hundred gigahertz would come from near the event horizon. And already at the time I knew there are possibilities to take telescopes distributed over the world to give you very high resolution. At the time I was calculating I was just estimating how large should that black hole be, and it was a bit too small. It was a bit fascinating. It was a bit frustrating. And then sort of there was one moment in like a few years later, I was going through a conference proceedings. I was trying to find a very famous paper, which was cited 1,000 times. Next to it was, or like two pages or a few pages before, was another paper, which was cited like since the 70s, 20 times, so completely overlooked. And it showed how a black hole would look like in front of a star. And it was much bigger than I had thought. And I thought, I forgot something. Namely the fact that black holes actually will magnify themselves. And I'll explain that briefly. But that was sort of an amazing, I call this in my book the amazing grace moment, because at that point it clicked, it will be possible. Because I knew there's radio emission coming from the event horizon, and it will be large enough. And that's when, this was 25 years ago or so, I'm 27 now, getting older, shoot. So how does a black hole look like? Well, that's how a black hole looks like. If you have a black hole on a dark background. So what you need to do, you need to shoot light at it. And luckily, so this is a black hole. Well, this is now a bowling ball. It's gray. Of course, a real black hole would be really black. But if you shoot light at it, what will it do? It will deflect the light rays. And what you see here is lights, your parallel lights being shot at it. And then you see how light is deflected because of the curvature of space-time. And if you go close enough, there's a characteristic radius of separation where light will be bent onto a closed circle. So you shoot next to the black hole, it bypasses, but then it will go around and stay an infinite amount of time on this circle. Which would mean if you would stay here, you would look in this direction, you would see your back, right? A bit distorted, but and you wouldn't stay long here, right? So that's but for a short moment, you could enjoy this sight, seeing yourself. Of course, I mean, looking at a mirror may be an easier way and more safer way to do this. But anyway, physicists love to do this in a different way. And that means every light that comes in from between here and here will be caught and captured and end up in the event horizon. So wherever you look from here to here, you always look into the darkness. And that's why the darkness itself looks brighter. And the light that goes outside will go around and come back. And so actually you will see some extra light coming from this side. And that will create a bright ring around it. So you have a darkness and a bright ring because of this. This black hole is also rotating, as you can see. And that's why light can also go backwards. Because the space is dragged along. So the light will go in this direction, then we go backward and disappear in the event horizon. So even if you look So far away here, it will be caught and disappear here. And then we calculated this, and we said, okay, let's assume we have this radio emission surrounding the black hole. It's illuminating at this particular frequency. How should it look like? And you see sort of in this characteristic radio is sort of a watershed outside the event horizon. It will create a really sharp, what we call then the shadow of a black hole inside a ring of light. And then the important thing is that the black hole itself, sort of the event horizon, will be much smaller than this, because the light capturing is much larger. And that made it just large enough to see with an Earth-sized telescope. You know, the size of the resolution of a telescope is given by the wavelengths divided by the size. So the smaller the wavelengths, the higher the resolution. The larger the telescope, the higher the resolution, the finer you can see. And the frequency was fixed, the wavelengths, so you can only play with the diameter. So if you know how big this is roughly the size of a mustard seed in New York, as seen from here. And you have wavelengths of about 1 millimeter. That you can calculate what the size of the telescope has to be. It had to be 10,000 kilometers or so, right? And that you can do. Now I always try to explain what the shadow really is. Just, you know, it really is not very special. It's like, you know, a teapot in a campfire, right? Or wick in a candle. Yeah, it's just the light that's absorbing. So you don't see the black hole itself. You see the absence of light. That's very important. But that speaks of the event horizon, really. Now, today we simulate black holes in supercomputers. What you saw here is a setup of a plasma with magnetic fields threaded, and then the magnetic field, the plasma will rotate around, like the planets go around the sun. The gas will also go around, and because gravity is stronger the closer you get, you have to rotate faster and faster. You will rotate faster and faster as the inner planets rotate faster than the outer ones. And that means that all the magnetic fields which are in there will be sheared and dragged apart, and looks like a spaghetti bowl in there. And then you let this process running. You have the black hole in the middle. And what turns out is, as the plasma approaches the central region, most of it disappears, but some of the magnetic fields will actually be wound up so strongly that they'll shoot out along the rotation axis of the accretion flow. And that means some plasma will be able to escape. And not everything, like 97% of the plasma will disappear, but 3% will be able to escape. So if you ever fall into a black hole, make sure you hold on to the right magnetic fields, then you're able to escape. So if that's the only thing you take out of this, so for advice for life, then you're safe. Anyway, this was sort of simulation how we do with plasma and magnetic fields. Then on top of that is radiation. How is radiation generated? Electrons are heated. They're heated up to temperatures of 100 billion degrees. And the magnetic fields are there. They deflect the electrons, and you start producing radio emissions. It's like a giant antenna, so to speak, with lots of radio emission going on. And then the light is created. The light is deflected, the light is absorbed. And what we're showing here is sort of how it would look like if I had all frequencies. And so I would see the accretion flow, I would see the plasma jet shooting out, and in the very center, I see the dark region, the shadow of the black hole. And you know, in the sun, of course, the central region is the brightest, but in the black hole, the central region is the darkest. And you have the brightest region and the darkest region. This is the darkest darkness you can have in the universe, really right next to each other. The most efficient energy production is here, and the darkest darkness here. Black holes are just extremes. Also, seen from the outside, as I said, time is stretched. Time almost seems to come to a standstill here. Yeah, so time, you know, everything that's hovering around a black hole will seem to be extremely slow, and so time will be extremely dilated. If you then zoom on to a particular frequency using these models, then what's left, you're sort of like X-raying onto the right frequency next to the event horizon. You will see this ring of light and the darkness. And that was a paper that we published. And so this other image was in 2000. This was the latest one in 2016, which predicted, you know, how the shadow of the black hole in M87 should look like, with perfect resolution, which we never have. And I already mentioned it. I mean, galaxies have a supermassive black hole, but also other galaxies should have one. And the bigger a galaxy, the bigger the black hole. If you go to the biggest galaxy, the biggest other galaxy in our environment, it is this galaxy M87 that you mentioned just before. It's 55 million light years away. This is a galaxy, and you see it's an elliptical galaxy. There are thousands of billions of stars here. And there's something sticking out here, this little thing that you see there. And if you go to a radio image, you see it more clearly. There's this plasma jet shooting out from the very center. And if you calculate the energy that's in this outflow, it's the energy of 1 billion suns. Yeah, 1 billion times the energy of the sun is just going into this plasma outflow. And it's all coming from the size of the region of a little larger than the solar system. And so the idea was, yes, this has to be a black hole as well. And then we did this experiment zooming in onto the two sources that I just said, the center of the Milky Way and this biggest galaxy nearby. And as I said, we need a worldwide telescope as large as the Earth. And what we do is we combine telescopes which are separated around the world. We actually store the radio emission locally on hard drives. And we tag exactly when the radio light arrives with atomic clocks to picoseconds precision. So the waves come in, we can record them on hard drive. And because we can record digitally the light on computers, we can do everything that a mirror would do with the light in the computer afterwards. We have all the information of the light in the computer. And so, a mirror would just reflect the light and combine it in the focus. So that's how it would happen. So we have this giant telescope. You just take those 2 points here, left and right. A light wave comes in. The mirror reflects, goes into the focus. Assume this is a point source. So this will be exactly identical waves. And what we will then see here in the combination is actually the interference pattern of these two waves. Yeah, the waves come in, and then you get the interference pattern when you overlay them. Yeah, your two waves are overlaid, you get interference pattern. And that's what happens if you do 2 points on the telescope. And interestingly, if you, and so that's what you see here, 2 things, and then you just get the interference pattern of 2 waves. And that, if you would have a big telescope, you would cover everything and just leave those 2 points open. That's what you would see. You would not get an image. You would just get this interference pattern. But now you take multiple points on this telescope because the Earth rotates, so the orientation of these, what we call baseline, will change. And it's like having different points on your telescope that you now open up. You take more and more spots. You've covered this mirror completely. You initially only have 2 spots that you use. Now you take more and more spots away that you get more and more parts of your mirror. And then what you see is you get from all these other points also interference patterns, and they overlap. And slowly, the image will emerge. The more spots you take away, the more cover you take away, in the end, you can recover the structure of that image. In this case, it's a teapot, not a black hole. So if that would have been a teapot, we would have been able to tell. You don't get a perfect image, but you get an image good enough to tell you the structure. You need to take some image processing to check that you're doing the right thing and to clean this image, but by and large, this is how it works. So it actually does exactly what an optical telescope does, just on a much larger scale and with less information. It's really a scratchy mirror. That's what we're using. You take a mirror that's completely scratched, and you get sort of an ugly picture, but you know exactly where the scratches are. And that's why you can use image processing algorithms to take out the effect of some of the scratches or investigate this. So we did this experiment in 2017, which was the first one where we had enough telescopes assembled worldwide. We put together this global collaboration, and these were the telescopes involved. This was in Mexico, Hawaii, South Pole, Spain, Arizona, and Chile. And actually from our team in Nijmegen, we had people everywhere. except South Pole, because South Pole is, you have to stay an entire night, which takes 6 months in the South Pole, so it's an involved process to go there. I was in Spain at this telescope in 30-meter because they had the best food in there, because they cook for you and so forth. So in Arizona, where I was before, you had to bring your deep-fried pizza. American, for 1 week, deep-fried pizza is not so nice. So I sent my students to Arizona. They love it. And then, so this is the team in Chile. This was the team at the beginning of the observations. This was after the observations. So there were 10 nights. It was really like we were observing, because usually you need good weather all around the globe. And we had like 2 weeks, and we had some days where we wanted to observe. And I came to the telescope, and Spain usually has the best weather, the worst weather during that period. I came there, blue weather, blue sky. And we started observing the entire night. Next one, perfect weather everywhere, observing. Next night, perfect weather, observing. Next night, some clouds. I think it's bad weather. Let's have a rest, right? So that was. I mean, you have to be lucky. Other campaigns before or later had much worse weather, and so we had perfect weather, and the experiment worked. Then, of course, you have to analyze the data, and this is a global collaboration. This was a collaboration meeting in Nijmegen in 2018, where we got together. These are about 120 of the 300 authors of the collaboration. That's where we discussed the image. So this was. We met here. This was the old chapel of the university, and then we were discussing and preparing the publication. And to make sure we wouldn't fool ourselves, we split up into different groups. For example, they would independently process the data and then compare in secret, and then compare, unblind the data and compare it to make sure we're not fooling ourselves. And then we would rerun the entire thing just computer guided, so that for the computer to tell us based on simulated data what is the best image algorithm processing. And it was so important to actually meet in person and discuss all this after all this, because this is global. We did everything by Zoom. Well, you know now, but this was before Corona. So we just got out of the EHT, with all these virtual meetings, 4 or 5 a day, and then got into Corona. This was sort of, we had Corona 2 years before, so to speak, in terms of virtual collaboration. And then came the big day when we were in Brussels at the European headquarters presenting the image, and because we were convinced this was right, and we've actually by now confirmed this in various ways. And so this is the image we showed. Okay, the music you don't hear. It's my son made that music. He's making film music. And so we're zooming from the heights of Chile into the constellation of Virgo now. This is a galaxy 55 million light years away. You see the radio emission measured actually from the Netherlands with a LOFAR array. And you see all these bubbles actually generated by this plasma jet that's shooting out. This is the picture taken by the Hubble Space Telescope. Now we switch over to lower frequency, very long baseline interferometry. We see the jet, we're following it lower and lower and lower, and suddenly there was this image. And you saw before, every time we saw jet, because it's self-similar. Yeah, it just expands over many orders of magnitude, from the smallest scales all the way to the outer scales of the galaxy. But when we reach the frequency that comes near the event horizon, we suddenly see that ring. And the size was exactly as predicted within the error bars, which is a factor 2. But the size was there, and we saw the ring and the darkness. And so that was a very moving moment, seeing it for the first time, but also being able to present it, to share it with the world. Of course, as you said, it was amazing. It was really all over the world, on all covers. The internet had a lot of fun with it. Like cats and black holes is not all of them were for minors, but okay. And And also what's also is nice is it was actually included in the collection of the MoMA, because it was sort of considered a piece of art to some degree now. And also the Rijksmuseum in Amsterdam has now a copy of that image. So it became an icon very quickly. And then this year, we finally were able to look into the heart of our Milky Way. That's where it all started with. The Milky Way is much smaller. And around this big black hole in M87, it takes 2 weeks to rotate for the gas to rotate around. So within a week, there's not much change. A little bit, but not much. But in the center of the Milky Way, it takes 20 minutes, 30 minutes to go around. So within a night, when we observe, when we expose, the things will wobble around. So we had to quantify that error. Actually, we saw that image already in 2018. Yeah, but it took us until 2022 to quantify the error. So it was only about the error. Yeah, that's what science is, to be able to quantify your error. Yeah, everybody can make an image, but to quantify an error, that's the hard part of it. And so, of course, in the end, you turn into a nice movie, right? So and that's now again this picture of our galaxy, and then we switch over to radio light. And this is how the galaxy looks in radio. We zoom into the very center, and now you're already very familiar with it. This is Sagittarius A region here with all the filaments, which are magnetic filaments, and that's where Sagittarius A West is, and we see Sagittarius A Star. Star means just a special source. And then when we zoom in with the Event Horizon Telescope, we suddenly again saw the ring. Well, some spots here, but by and large, it was exactly the right size as predicted by the mass. Because in this one, we know the mass to 2%. Actually, even better than 2% by now. We know exactly how large, and the size of the shadow is directly related to the mass. So it was after M87, it was a clear prediction what we should be seeing, and we saw it. And so that, I think, was a very nice confirmation. We also, and just now for the physicists here, we compared that to models. This is a simulation now. This is a magnetically dominated accretion flow with actually R high means that a lot of energy is in the emission is in the jet. And then you look at it from different inclinations. This is from the side, and here you look from the top, and you see a black hole can look different depending on from which direction you look. And then this is a spinning black hole, a maximally spinning. This is a mild, non-spinning black hole. And so we are calculating really, literally millions of images in this, and many different models. This is disk-dominated. This is jet-dominated emission. This is less magnetic fields. So all these are massive supercomputer simulations. This is some maybe undervalued part of this collaboration. I mean, just doing one of these like 10 years ago was a major achievement. Now we make massive libraries of those, and we can compare them and look which one fits. And that's what we do here. We just look at which one fits the predictions. And you see all of them have a shadow. That was a key prediction. The key one was we can see the shadow. So the size was fitting exactly. So all of them had the right mass, so that the size fitted. But the shape already rules out a lot of these models, because the shape we had. Then we look at some other emission at different scales, which only in the end only those two models would survive and would be fitting the data. But on the other hand, there are two models which are actually able to explain almost all the emission, from radio to near-infrared, the size, the shape, and all the things. And that I find is quite amazing. We can, from first principle, simulate a black hole, and it fits what we observe. And so this is, it's a little bit of self-servicing, I think, but this was a prediction. This is 2019 and 22, and this is just, it doesn't happen often in astrophysics that things work out so nicely. And it works because, in a way, it's simple physics. Black holes are actually simple compared to everything else. Black holes are much simpler than an ant or a cell. They just consist of two numbers, the mass and the spin. That's all. And all the speeds and the temperature are set by the speed of light. And so that's why this is possible, because it's simple physics. It's complicated math, but the underlying physics is not so complex. And then one other thing I love, let's see how much time I have left. I probably have to wrap up quickly. But this here is the mass of the black hole, and this is the inferred shadow size. As I said, in the theory of relativity, the larger the mass, the larger the shadow. It goes linear, it goes perfectly linear. And this is not a fit, this is a prediction, and that's what we measured with M87 within the error bars. Then, as you may remember, there were gravitational waves measured 2015, and interestingly, gravitational waves, when two small black holes merge, they are produced also at this region where the shadow is produced. The gravitational waves also measure essentially the shadow size in an indirect way. So if you overplot then where the gravitational waves fit over 8 orders of magnitude, they fit the same simple theory. And then, of course, okay, 2 points always fit a line, right? So now we have such a star, and within like 20% error bars, actually 15% error, they fall exactly on this over 8 orders of magnitude. I think that's the beauty of relativity, of general relativity. And that indeed, shows that black holes are simple in a way. So what we'll do in the future is we hope to expand the array. We want to build the telescope up here. Just 2 minutes ago, we put in ERC grant, another one. We just found out we're only on the reserve list, so I don't know whether it's going to happen. But if that's here, that telescope, we can actually expand the event horizon, add new connections. And we know stuff is going around. We just recently discovered indirectly a blob going around the black hole, and we can actually measure the speed and maybe measure how energy can be extracted from the black hole. This is one of the things we still want to do. So we want to go from still images to a movie. That's one of the future things. So let me summarize, and I'll still wrap up after that briefly. I think we've seen the shadows twice. I think we can now safely say black holes are real. And we see, within the theory of gravity, the shadow really is the signature of absorption by the event horizon. General relativity holds over 8 orders of magnitude, which I think is an amazing feat. We understand the astrophysics better. And we actually see in the simulations that these plasma jets extract energy from the black hole spin. There are some interesting effects that we seem to infer there, but we still need to prove them. That's one of the next things. So the next step is we're upgrading the Event Horizon Telescope, and I think we have a fantastic laboratory. We understand astrophysics near black holes. To some degree, maybe understanding black holes at some point better than our sun. The sun is very complex, and a black hole is simple. So maybe that's possible. And really, I think what has changed in the last 10 years, we are really in an age of space-time physics, experimental space-time physics. It's no longer theory. It's not just math. We're measuring it. I think that's an amazing step in physics. Now, if you look at the large scale, and we're looking at the end of space in physics to some degree, and in the end of science to some degree, because we're going to the event horizon. Are we able to transcend that event horizon? It's a big philosophical question. So we're going to the edge. Can we go further? And it's hard to say. All these, this is the Hubble deep field, also already more than 20 years old. It's one little piece of, you look through the eye of a needle that you hold to the sky. It's filled with thousands of galaxies. So there are hundreds of billions of galaxies. All of them have hundreds of billions of stars, and all of them have a supermassive black hole at the very center. The universe is full of black holes, full of these frontiers. And as we know, and they are sort of the end of space and time. And we also know, the universe had a beginning, in the beginning. A frontier that is, in a way, very similar, very dense, very compact, everything, coming from, not really, it's sort of a very small region where the universe was expanding. And sort of physics inside a black hole in the beginning of the universe may be related. But they both also represent a fundamental limit to how far we can go. And I think that's good, because it means there are still questions that we can ask. And maybe there's some questions we'll never get an answer to, which is also okay. I think we'll have to, which still leaves room for us humans to dream, to think, to love, to hope, and to believe. Thank you.
Thank you very much for this really fantastic and inspiring lecture. I think that you explained so many topics so clearly, and I don't think this academic year I will have to read my classes. So, are there any questions, please, from the audience? Yes.
So, I really don't study this, so it's probably a very naive question, but I'm really interested in the image processing algorithm. So what's probably happening is you collect the radio data, right? Yeah. And to get the image, you do some sort of Fourier transform or some intensity mapping, right?
Yes. So now, not intensity, we actually record the phase as well. Because we have the radio waves come in, and we record amplitude and phase of the waves, so we have the complete information.
And in optical, quite often you do just amplitude intensity interferometry, which loses the phase information, which is a key image information.
Okay, so once we have that image, and then we are trying to compare with some simulation.
Right.
And then, so on this process, which one do we trust more? The data analysis pipeline that generates the image, or the simulation? Which one we are trying to fine tune?
Oh, well, they are completely independent.
So we do the imaging completely independent of the simulations. And then afterwards we compare, in fact, we compare not the image, we compare the UV data, so before the Fourier transform, we compare. So we take the image and compare it, we take a Fourier transform and compare them. Yeah.
Questions? I have one.
The boss has one, so
Thank you. So you've shown this amazing agreement between the model predictions and the actual observations. What me as a non-astrophysicist wonders is into the models. Is there any other input than general relativity?
yeah, absolutely. I mean, none of these models, that's why we showed the different parameters, there's some uncertainties. One important one was this height parameter.
And that means, and that parameterizes where are the electrons heated. And so the acceleration of the electrons happens on microscopic scales, much smaller than we can simulate. And that's the biggest uncertainty. How are the electrons really accelerated and heated? And so we have some parameterization, and which I think are reasonable, but they are certainly not far from complete. When I say we can explain everything, there's one thing that we are not very well in explaining, and that is the variability of this. And so our models are actually slightly less variable than the actual observation. It's not a big distinction, but there's some more flaring in the real world, and this probably has to do with some extra heating, acceleration of particles, which is happening on macroscopic scales that we cannot cover. So there's still a lot of things to be done. But we do start with, you have general relativity as a background, and then you have hydrodynamics and magnetic fields, and you assume the magnetic fields are frozen into the field, so there's no dissipation of magnetic fields, which in practice there will be a little bit by and large. But then it's mass, energy conservation, and the normal hydrodynamics. So that is really from first principles. But you need to start with an initial setup, of course. What's the initial conditions? Luckily, there seems to be sort of, and so how much magnetic field is there? That's one thing. But it turns out, it seems to be that there's a pile-up. So once magnetic field starts to be amplified, and it gets to a maximum point, because when it's too strong, it actually will stop the inflow. And so there has to be sort of a maximum. It seems to be that these black holes tend towards the maximum, which takes the parameter away in a way. That makes it also easier. Yeah, what's the microscope, the particle physics, and that's some of what you guys are also studying here in Auger and other places with CTA, it's, how are the particles accelerated.
About magnetic field, don't we need to account for some effects of non-linear electrodynamics, in the sense when the magnetic field becomes quite close to the critical value? Quite close to the critical value, so that energy density of magnetic field is close to the energy of star creation, something like that.
You would think so, but
by and large, these magnetic fields are not very high. We're talking about a few Gauss. and it's not a neutron star. And on a neutron star, you have these magnetars which have tens of 14 Gauss or whatever, or 15, then it becomes critical. But the supermassive black hole is actually very benign. I mean, the other thing I always like to tell students is, I mean, if you calculate the average density of a black hole, it's just the volume of the event horizon divided, the mass of the black hole divided by the volume. Now, since the radius grows linearly with mass, then you have mass divided by mass to the 3, or the volume goes with a cube, which means that the average density of a black hole decreases with 1 over the mass squared as the mass becomes bigger. And so if you fill the Earth's orbit with water, it will be a black hole. Right? So, and the average density of M87 is actually less than air. You fill the solar system with air, you have a black hole. And of course it will collapse. It will collapse because of the gravity is so strong, but the average, that part of the physics is not that exotic anymore for supermassive black hole, and neither are the magnetic fields.
Maybe my question now. So you showed that there are 2 models which survived all these models because they are in agreement with the observational data. What is the difference between these 2 models? So whether you will be able to tell them apart? What is the
No, I would still be careful.
I mean, because it depends on how good the models are, right? And none of the models is perfect. As I said, the variability is not perfect. So I would, so this gives us a direction. This was the first time we were able to say this. And it looks like these MAD models, these magnetic dominated models. And it seems that the spin models are preferred. I think we want to test them more strongly before we make a very strong claim. And I think the shadow and the size is a very solid measurement. The astrophysical one is much better than people think. But I think we want to explore them more and make it more solid to quantify the error. The difference here is the spin, largely. And we're also not doing it very finely. We're doing very rough grid still. I mean, we could still do it much more finely and do a much better fitting. And we have much more information that we also don't take into account. But my gut feeling is that we are going in the right direction. There are independent evidences. For example, this is more face-on. That this black hole is, we're looking sort of into it. And there are other measurements which point into a similar direction. So let's talk about this in 10 years, and I think that will survive. But
so I wonder, you were measuring from 2 points, no? So
No, we had 8 telescopes in 6 different locations.
So how precise was this the angle to look?
Yeah, it has to be, the separation
has to be known to be better than the wavelengths. In fact, a tenth of a wavelength, and the wavelength is 1.3 millimeter. So you need to calibrate the separation of these baselines to 20, 30 microns.
This is enough to show such a small
Yeah.
object so far away.
Yeah, so and that, I mean the world is pretty big, and so the angular differences on this is something you can measure, but
It requires atomic clocks with sort of sub-picosecond accuracy, and you can calibrate them. In fact, you use the quasars and the source itself to calibrate the errors, because the clock errors have a very different time scale than, for example, atmospheric errors. The atmosphere, it's actually the biggest enemy is the atmosphere, because the radio waves, millimeter waves, are going through humid air, and so the arrival time is slightly different, and it changes on time scales of tens to 20 of seconds. And that's why really you have to calibrate on 10-second time scales, and then you correct the atmosphere. Luckily, you have a network of telescopes, and so, the cloud that affects this telescope will affect the combination of those 2 telescopes and those 2 telescopes. And then those 2 are also affecting each other. And so using this triangle, you can actually calculate out what the atmosphere doing is over a single telescope. So, and that's part of this entire calibration strategy.
Just a short question. Is there an idea in future to use space combination of telescopes?
Absolutely. That's actually, I skipped
these slides, unfortunately, but we have the proposal that we have 2 to 3 smaller dishes on an orbit around the Earth. Doesn't have to be the moon, because that's too large. You're resolving out everything. So, and then as they are orbiting around the Earth, one goes faster than the others on slightly different orbits. And so they slightly differ apart. And so you have all orientations and all separations. And you get perfect images. I mean factor 10 razor sharp images you can do from space. But I mean, it's a few $100 million more. And I'm trying to get this stupid telescope in Africa, just one, right? So, I mean, not a stupid one.
So. Any more questions? There is one question. Please shout if you can.
My question would pretty much be if it would be possible to still better the resolution of the images.
Yeah, well, one way would be to go to even higher frequency. So we are now doing attempts going from 230 gigahertz to 345 gigahertz. So it gives the smaller wavelengths, higher resolution, but the atmosphere is much worse. And so that also the signal to noise goes down. And the signal to noise also factors into your image, right? So you have a higher resolution, but much more crappy and more noise. And so it's not going to be much better then. But you see a little different frequency, maybe some more finer structures. And then, yeah, you have to go into space. You have to make a larger baseline because for two reasons. You cannot go to higher frequencies. The Earth is not transparent anymore at these high frequencies. That's one reason to go outside. And then the baseline becomes larger. So you can improve two things, smaller wavelengths and larger baselines in space. We also have some from school, some students here. So you should also have some questions.
So you can think about it. So I want one question from the first row here.
So regarding this feed to the prediction, so I was just wondering if this feed would kind of disprove the modified gravity theory, then if it's matching so well with the observations.
Yeah, well, modified gravity typically happens on larger scales and lower accelerations. But there are modifications, there are non-scale-free modifications to gravity, alternative theories, and they have sort of bumps in between. I've seen talks like this, and then of course they fit the bumps, so they just fit in between the three, right? So, but that's a unique thing of gravity, that it's really completely scale-free. And any deviation from this linearity would disprove GR. And indeed, the question is this modification strong enough for supermassive black holes? If you have a quantum gravity modification to general relativity, it could be just a minor Planck scale modification, or it could be something on the Schwarzschild scale, which is the event horizon scale. That's what we can test. The other one we cannot test. So there's still room for a lot of fantasy. But of course, this model passes almost everything with flying colors. So, you have to have strong arguments to say why you come with a new one.
So I think we have a question from the students.
Good. Yeah, I can hear that. Oh, good question. You could do the same. Yeah, you could do this. The only thing is they would change the length very quickly. So then, if they go together, then they will, only gradually become larger and larger. And so that makes life easier from an experimental and calibration point of view. But if they would go the other way, like in 4 hours, you would have all baselines covered. That would allow you to make faster images. Yeah? So that would be a good way if you want to do fast images. But then you need to be able to measure within a few minutes everything. Every second you have to make a good measurements. And then you have to have built bigger dishes to be able to make an exposure within a few seconds, rather than within an hour. And so if you pay me a dish which is sort of like 20, 30 meter, I will do that. And I'll say it was your idea, and then It would be better. I think it would be better, yes.
Thank you. Any more questions?
Well, it's more expensive.
What about antimatter, and black holes? Is that primarily theoretical?
Yeah, no, that's, first of all, antimatter would also make the black hole grow. So the black hole doesn't care. If you throw antimatter into a black hole, it will just become bigger. And then there's the opposite of black holes, which is the white holes, which sort of where nothing can go in, but everything just goes out. And theoretically that exists. And if you connect a black hole and a white hole, you get a wormhole. And so that'd be great for science fiction. I'd love to have that. But there's no evidence how these things would come about, that any of them exist. So at this point, there is no reason to assume. I mean, that's why, just to make some advertisement, I wrote a book. So if you want to read up all the it's not in Slovenia yet, in your language, but maybe it comes. So there's the English version. And I said, so the task of the mathematics, you can think of everything. In mathematics, there is sort of every unicorn, not every unicorn is possible, but many things are possible. It's up to the physicists to find out what part of mathematics is actually reflected in the real world. And if I allowed one more philosophical remark, for example, which I find amazing, the mathematicians introduced complex numbers. Yeah, you take the square root of -1, you get a complex numbers. And out of this comes a positron, an antimatter, comes out of complex numbers. It's just amazing. Just some mathematics suddenly shows up in the real world. And then you have black hole and white hole, also is in the mathematics, but does not seem to be realized. And so that's what the physicist needs to do, figure out what is real and what is not. I mean, mathematics makes predictions, and physics needs to measure and find it. And so some things remain unicorns, and others become real horses. So.
I think there were more questions.
But maybe at some point, maybe in 20 years I'm wrong, and someone finds a white hole, right? So then I'm.
When a star collapses and all the mass reaches one point, is it because of the gravitational force, or is that cause the increase in gravity?
Both. It's a runaway process, right? So the closer, the smaller it is, the stronger the gravitational force, the more the collapse. So it really is a self-propelling process. That's why it cannot be stopped, unless another force emerges that we don't know yet. That's, yeah.
One more in the back.
Just a simple question, I think. So given the current rate of our technological development, when would you expect or predict the video of the black hole would be created?
Well, we just found one event in our data, which probably was a very pronounced event where you had a strong thing going around for like just one orbit. And it just happened, and that we have like 1 hour of the array where we could make such a movie. Yeah? And that happened 5 hours before we had that time scale, because the Earth rotates, and then at some point we have more telescopes in sight. Had we had that telescope in Africa, we would have been able to see it. We didn't. So, it's a question of luck, statistics. But I think in the long run, to do it really properly, we really want more telescopes. So it will take a few years. But if you're lucky, it could already be in our data, because we took more data in 21 and 22. And but then you have to be really, really lucky. And then it's just one, and yeah.
Thank you. So I think we all look forward to new results, new images, and maybe also a movie.
Yes, but you have to take a long breath sometimes, right? So.
Thank you very much.
Okay, thank you.